All right, so in this part, I have focused actually on giving you some explicit examples that include both simulations and measurements. And I have purposely chosen to work out on some designs in which case some things work well and some things don't work well. So we can basically summarize and see what can go wrong. So what we have basically covered so far is going from the available transfer function to our coupling matrix diagram, finding the actual coupling matrix synthesis approach, and then, of course, calculating S21 and S11 in the normalized frequency domain. In this particular case, I'm going to focus on a third-order filter, and these are going to be the coupling matrix values that all of you should be able to calculate by now for a simple third-order Chebyshev 20 dB ripple at 1 gigahertz with this much bandwidth, right? So this is something that it's basically textbook, and all of you should be able to do that. Then we have basically learned that I can start synthesizing the actual circuit that will implement this by essentially using inverters, right? Here, basically all the inverters we need. We need 4 inverters for a third-order filter, and then by using these normalized components that will very quickly become resonators once we denormalize this from this domain to the actual frequency domain. I think I'm going to skip that slide. This is more about as an FYI. Once you have the low-pass prototype, as we've learned before, you can apply this bandpass transformation to denormalize things. And you also need to do the correct impedance scaling, which for this example, I'll do the normal thing. The impedance scaling will go from 1 to 50 ohms. So this is an explicit table that shows you exactly how the parameters will change. So our normalized elements basically will become LC resonators. For right now, these are considered ideal shunt LC resonators, and the values for both L and C are given here, where Z0 is our 50 ohm impedance, fractional bandwidth is whatever we're doing here, and F0 is also the frequency of interest. Maybe I should also emphasize here that these inverters that we discussed before are also being scaled when you scale from the normalized frequency domain to the other domain. And they're also being scaled when you change the impedance. For example, as you have seen before, and you can go back to your notes, when we go from the ideal inverter to the inverter that has to match a 50 ohm impedance, you actually have to divide the value by Z0 or 50 ohms, as in this case. So that's basically our first scaling, which practically will now yield us this filter. So now you know basically everything in this filter. You know that if you were to do this with an ideal inductor, it would have been 0.79 nanohenry based on the equation I just gave you before. You know the exact value of the capacitance, and now you know the new denormalized coupling matrix values that are basically the inverter values for these guys. Now from this point on, it basically becomes a realization question, which is what I want to focus this discussion on. First, we have to realize somehow those inverters. So the question is, what physical structure are you going to use to realize exactly these inverting values? And second becomes the question of how you're going to realize your resonators. In this case, I'm going to basically use, I'll come back to this slide in a minute, jumping a little bit ahead, but I just want to show you. In this case, I'm going to use transmission lines, 90 degrees transmission lines for the inverters. This is one of the simplest possible inverters you can use. And the open circuit stubs for the resonators. The open circuit stubs I'm using here because I have used it before. And so I hope you guys will go back and consolidate your knowledge, because we have actually derived that equivalent circuit for the open circuit stub when it resonates at the second resonance of 180 degrees. So the question here will become, calculate these values, Z1, Z2, for the inverters. We already know the electrical length, it will be 90 degrees at resonance. And then calculate these values, ZR, the resonator values. We already know the physical length, it will be 180 degrees. So basically, once you know the inverter values and once you know the LC components, in this particular case, we just have to find 3 numbers. The numbers we must find are written right here, Z1, Z2, and ZR. Now, before I do that, let me show you a couple of things. First of all, I want to remind you that the values of these elements is totally arbitrary. So if you come up with a calculation we just did, and let's say you're not happy with the 0.79 nanohenry, you can immediately scale it with any number you like, as long as you scale both L and C. And the only thing you have to do now is basically scale these inverter values. Equivalently, it might happen that you don't like these inverter values actually. Why? Because as we'll see later on, they might actually yield an inconvenient impedance calculation, in which case you could go back to this filter and scale everything with a factor of k and recalculate everything. I'll show you, I have purposely chosen an example here to specifically highlight this because it happens so often in real life. Also, this is a simulation here that assumes the denormalized bandpass filter in its ideal implementation, so you will see zero loss and everything looks nice. All right, so once we made that choice, once we make this technology choice, now it's time to calculate things. So let's go here step by step. First of all, the way you basically calculate the impedance value, we have already done this, this is just a reminder, is by essentially matching the ABCD matrix of the 90-degree line to the ABCD matrix of the ideal inverter. So we already know the ABCD matrix of the transmission line is actually shown right here. We already know the impedance inverter ABCD matrix. And at resonance, they actually are exactly the same. And as I said before, that basically gives you that Z should be equal to K. So the impedance should be equal to basically the impedance inverter. Here we, of course, are using the J, which is 1 by K. And so clearly, once I have these values here, my Z1 and Z2, the two inverter values, will be 1 by M, or 1 by J, if you will. And we are basically at luck here because the values come to be amazingly good. I would put perhaps 3 exclamation marks here because they come to be close to 50 ohms. I mean, what else could be better? So you can very quickly basically do that. So you can take, for example, a microstrip line, vary this W until you hit 46 ohms and 48.5 ohms, and that's it. So this is what I've done here. So I've taken now the full circuit that you saw before, simply replacing the ideal frequency-independent inverters with the more realistic transmission line inverters that are lambda by 4. Once I do that, you can see essentially this black line, which shows the new response. So before we discuss what happens out of band, let's focus a little bit in band. So once you do this in band, you will find that the response is almost what you want. It's very close. It's actually amazingly close, but it's not quite. So this one is a little bit narrower filter. And so that means you have to do a little bit of tweaking. Now, some people decide to do the tweaking or the optimization at the very end of the filter design process, so they will just leave things as they are. Some people will actually decide to do it step by step. So the optimization that we need to do here, if you decide to do it that way, is you need to change basically the Z1 and Z2 slightly to basically bring this bandwidth back to what it needs to be. So this slight change of Z1 and Z2, if you decide to do it, will basically give you these new values of 44.3 ohms and 42.5 ohms. And now, if you do the resimulation of this, you will get basically an exact bandwidth to what you need. Maybe it's a little bit too extreme to focus on these details here, but I'm just trying to show you every question that you may have as you go through. Now, let's talk a little bit about the out of band, though. The out of band is an issue because what happens again is that when you're using an inverter that is simply 90 degrees and you move enough, sufficiently away from that, basically you don't have an inverter anymore. So what you will see, and we'll see the out of band rejection later on, is you basically will start creating spurious bands. So this will basically be our first spurious response that will appear later as well. And unfortunately, as long as you use transmission line, there is nothing you can do about it. You simply hope that now annoying signals will exist there. Now let's talk about the second part. So the second part is how I'm going to implement this LC shunt resonator. So as we've learned before, if you take an open stub and you use its second resonance, it basically appears to be very similar to this LC. And in fact, you can use the design equations I'm showing you here to get the exact capacitance and inductance as a function of L and C. The way to do this is very simple. Is to literally calculate the impedance or the admittance, ZR or YR for this case, and make it the same of ZR or YR of LNC at resonance, right? So once you do that, you will extract these two equations, and you can basically use now these equations to calculate the impedance that you like, ZR. So that's exactly what I did. I know that my capacitance was 31.83 picofarads based on what I said before. I calculated my ZR impedance, and here instead of 3 exclamation marks, I'm going to put one pretty sad face. Why am I putting a pretty sad face? Is because, as we have learned, this is a practically non-realizable impedance. If you go back to the primer on design, we have basically learned that for most transmission lines, you can perhaps get between 20 and 100 ohms. But if you try to implement an impedance outside of this bound, you will come into big trouble. For example, if you try to implement a transmission line that is less than 20 ohms, the transmission line will end up being so wide that will basically start radiating. It starts becoming more of an antenna than a transmission line. And you will see this here in a minute. Now, in theory, you could go back to what I said before and rescale things and say, oh, okay, this is too bad. I need this impedance to become quite a bit higher, at least 20 ohms. So I'm going to rescale things, everything by factor K and try again. I didn't do that here because I wanted to show you what the effect is. Before I show you the effect of the impedance, this is a really interesting graph because it will help us explain the out-of-band response. This is a graph that basically compares the reactance, the resonance essentially, that my transmission line gives me versus the resonance that my LC is giving. The resonance that the LC is giving is actually this black line here, while the resonance that I'm getting from my transmission line is this red line here. So right at resonance, basically at 1 gigahertz, the two are identical. And in fact, this is a nice view that is zoomed in very close to resonance. So I would say if you look at the resonance plus or minus 10%, you basically have nothing to be afraid of. Things are pretty close. But if you look at basically what happens at 0.5 gigahertz or 1.5 gigahertz, you basically have big trouble. And so you can expect that away from resonance, your response will be nothing to what you expect. So in fact, this is the full simulation now by having replaced my inverters with ideal lambda by 4 transmission lines and having replaced my LC resonances with ideal stubs. Here I still have not done any microstrip simulations. Everything is ideal transmission lines. And already you can see that you start getting some spurious responses far away from the filter here and here. So these are the final values, the 3 values that I wanted to find. And let's see what the result is. So here's the layout that I will need. And hopefully this layout will bring a smile to your face because this is the width that I need for a 50 ohm impedance. And this is the width that I need for the 7.8 ohm impedance. So here you can see what I was basically explaining yesterday. I mean, just a minute ago. Yeah, we can, push things, but there is a point beyond which things simply become ridiculous. So if you were to basically simulate this using a full wave electromagnetic simulator, you will see effects that you wouldn't like. So nevertheless, in theory, you can simulate this with microstrip line. And there are models in ADS that will allow you to simulate this in microstrip line. And you will basically get the response that you see here. So again, this is not a full wave simulation, but it is a simulation using the microstrip results from ADS. So first of all, you will see an increased insertion loss right here, which of course is to be expected. Plus, you will see all of these annoying spurious responses. And in fact, this figure here is the one that will show you what happens in a very broadband sense. So our resonance is right here, 1 gig. But you will basically see a repetition of resonances every time these transmission lines resonate. So you will see it at 2, at 3, at 4, and so on and so forth.